This video presents a simulation of ammonia production and outlines the process, thermodynamic models, and energy analysis. Looking to the global models, we had to choose between equations of state and activity coefficient models. EOS is suitable for gas phase, nonpolar to mildly polar mixtures, and high pressure and temperatures. Activity coefficient is suitable for liquid phase, strongly polar mixtures, and moderate temperatures. For the global model, an equation of state model was chosen. RKSBM is most suitable as our feed is mildly polar and the process undergoes high pressures and temperatures and is recommended for petrochemical application. The feed is at a pressure of 5 bar and needs to be compressed to 40 bar. Thereafter, it enters an adsorption column containing of zeolites made of a pearl gate. The column is operating at 40 bar and 10 degrees Celsius. 99% of the hydrogen sulfide at these conditions is adsorbed. Modeling a pressure swing adsorber is not available on Aspen, therefore we are using SEP2 to model the desulfurization unit. A separation factor of 99% for hydrogen sulfide at those operating conditions is observed, which was obtained from literature.
The reforming section consists of autothermal reformer and exchanging reformer with an 85-15% natural gas split fraction into them as suggested by Handel Topsoe Corporation. The autothermal section is simulated by two adiabatic reactors in series operating at 25 bars, each representing partial oxidation and steam reforming reactor sections as can be found in a conventional ATR. The respective conversion of 70 and 80% give a high overall conversion of 94%, matching the literature value, and a close energy balance, a characteristic of ATR. Oxygen is completely consumed and streaming to continue to enter the exchanging reformer operating at 35 bars suggested by literature for a further 33% increase in hydrogen capacity. 99% overall conversion of natural gas is achieved. R-stoic reactors are chosen due to the lack of kinetic data in this preliminary stage.
The stream leaving the reformer enters a membrane unit which is operating at 6 bar and 30 degrees Celsius and separates 99% of the natural gas liquid. The NGL's feed stream carries on to the CO shift reactor and the NGL stream is transported. Modeling a membrane separation unit is not available on Aspen, therefore we use a SEP2 unit again to model the NGL separator. From literature, 99% of the NGLs are to be separated at those operating conditions.
Synthesis gas from the NGL separator will first enter the high-temperature shift reactor operating at 400 degrees Celsius and 25 bars, where the primary conversion of CO into CO2 will take place. The outlet stream enters an intermediate heat exchanger to lower the temperature down to 20 degrees Celsius. Afterward, it enters a low-temperature shift reactor operating at 200 degrees Celsius and 25 bars, which is where the rest of the conversion will take place. At this stage, we are using our Gibbs model to simulate fixed bed reactors typically used in CO shift reaction. Aspen determines the product of the equilibrium reaction subject to the stoichiometric ratio and find a solution that minimizes the total Gibbs free energy. Because inerts were specified, our Gibbs was able to give us an accurate simulation result with no side reaction taking place.
CO2-rich gas is first separated from water in a flash drum before entering an absorption column operating at 37 bar and -4 degrees Celsius with propylene carbonate as the solvent. CO2-free gas leaves the top of the column and proceeds to the methanation unit, while CO2-rich liquid leaves the bottom and the solvent is regenerated through two flash drums in series before recycling. 10% of the recycled solvent is purged to prevent a buildup in the column, while the rest is pumped back up to operating pressure and mixed with enough fresh solvent to maintain optimal separation. To produce food-grade CO2, vapors flashed during the solvent regeneration go through cryogenic distillation at 10 bar and -50 degrees Celsius. A compressor and liquid nitrogen cooler are used to achieve these operating conditions. The top product is disposed of appropriately and not flared as the stream is highly flammable. The bottom product is 93 tons per hour of 99.9% CO2, which is an 80% recovery of CO2 from the feedstock. This is then heated to 20 degrees Celsius for ease of transportation and storage. We model the absorber using red frac to specify the inlet stages and remove the condenser and reboiler from the column. The cryogenic distillation column is modeled using DSTWU with UNIFAC as the localized thermodynamic model. This is because equation of state methods use extrapolation to calculate the bubble point at extreme conditions and could give unreliable results. As such, we use an activity coefficient method. Operating conditions for the absorption column were decided by finding a local maximum through trial and error. We varied the operating pressure from 13 to 69 bar as advised from literature sources and found the best separation is achieved at 37 bar. We used the same method and referred to literature sources to find the ideal operating conditions for the cryogenic distillation column to achieve food-grade CO2 product.
Synthesis gas from CO2 removal section enters a primary reactor operating at 250 degrees Celsius and 37 bars. This is to reduce the concentration of carbon oxides one last time before entering the ammonia synthesis section. The outlet stream then enters a drying unit to remove excess steam before being fed to the next section. Similar to the CO shift reaction unit, We are using our Gibbs model to simulate fixed-bed reactors typically used in methanation process. Inerts were specified to prevent side reactions, and Aspen was able to give us an accurate result. Meanwhile, SEP2 column was used to simulate a drying unit. The split fraction of steam was chosen as 1 because an industrial dryer can typically remove all water.
For the ammonia synthesis stage, syngas from the methanation stage will be split. 70% will be compressed to 250 bar for the high pressure reactor, rest compressed to 150 bar for the low pressure reactor. A total single pass conversion of 47% of hydrogen has been achieved. The implementation of the discussed turbine on our appraised report has generated 9.9 megawatts of electricity. This will be used for the compressors. Using coolers and 2 parallel flash vessels which operate at 85 bar and 70 bar produced a rich in ammonia liquid stream. Since vapor streams V1 and V2 contain around 1400 kmols per hour of ammonia, we introduced a third flash vessel to further separate ammonia from syngas. Trial and error has been used to determine the optimal conditions for this flash vessel. Transporting pressure for ammonia is 10 bar, so all ammonia liquid streams have been fed into a fourth flash vessel to produce liquid ammonia at 10 bar. Purity requirement was not met, so hollow fiber membrane tubes were used to achieve the 99.5 weight% requirement for anhydrous ammonia. The vapor streams leaving the flash vessel is recycled, with 5% being purged. A heater was introduced to make the recycled stream all vapor phase. In this simulation, R-Gibbs was used instead of R-equilibrium, even though the reaction is reversible. This is because R-equilibrium assumes the reactor achieves equilibrium, which is not a valid assumption for our process, as we have decided not to operate at equilibrium conditions. Our simulation converges with the warning at the reformer stage as mentioned. The process meets all requirements. The following table shows the process units which consume or generate energy. The total heat generation is 70 megawatts more than the heat consumed. This is expected as all reactions besides that in the reformer are exothermic. Ammonia synthesis reactor and CO2 removal dryer are the highest heat generating units at 82.9 and 84.5 megawatts respectively, whereas the high-pressure ammonia synthesis compressor consumes 108.2 megawatts and WGR compressor consumes 67.2. Looking into energy savings, the reformer reactor outlet at a temperature of 760 Celsius will heat up the natural gas stream from 230 to 532 Celsius. Implementing this heat exchanger has saved 35.3 megawatts of heat energy, as the product stream heated in the reactor will preheat the feed that goes into the series of reactor. Furthermore, the introduction of turbines in the reformer and ammonia synthesis stage has produced a total electricity of 16.5 megawatts, which can be used in the process.